Hi, Stacy. Looks like I am muted. Is that true? I'm not muted. Stacy, I think you're muted. I don't know if you're talking to me or.
Yeah, I joined and then I got kicked off and then I had to rejoin.
Okay. Looks like we've got a lot of people coming back. I'm curious to see what our heat map looks like. Kind of all over the place. All right, looks like we're all back. I only have 13 responses. Did you go ahead and click on the screen? So the way to do it is just tap on the part, which hydrogen on the screen you think is the most acidic proton in that structure. And I want you to think about why. Hopefully I have a chance to discuss that in your group a little bit. 15 responses. I think we have more than that. Probably have close to 20 people. Do you have to hit the submit? Is there a submit option on that as well? Okay, so click on the screen and hit submit. There we go. Now we're up to 20 responses. Okay, so here's what our responses look like. Can you see the heat map I just pulled up? Yes, you can see it. No, you can't see it. No, you can't see it. Okay. There are, interestingly, 3 main spots. So let's take a look. The 3 main spots that people highlighted were this oxygen, which is interesting. Proton means H plus ion. So let's make sure we got our terminology down. So it's not going to be an oxygen, so it's going to be a hydrogen. The other 3 that were selected was this hydrogen out here, this one at the bottom, and then this one on the far left of the screen. The one that is most acidic out of all of these is the one on the far top right. Does anyone want to venture as to why this proton here is the most acidic? Meaning if it goes in water, it's the most likely one to be released as an H+. Who wants to share why that one might have been picked?
There's going to be resonance between those 2 oxygens.
All right, fantastic. And so this is a bit more of a orgo topic, but it relates, it basically brings together the topics that we've all worked on. And so what Jesse is talking about is that when this hydrogen leaves, so we get red instead, then we end up with this O having an extra lone pair of electrons. That means it's going to have a negative charge on it. The thing that is that makes a hydrogen able to leave is if whatever it leaves behind is stable. The more stable what it leaves behind is, the more acidic that proton is, and the more likely it's going to be okay if it leaves. So here, having a negative charge is never a good thing. It's never very stable. But the question is, what is the most stable negative charge to have? Some of these other ones over here, it would have been a negative charge on a carbon, but we don't have 4 bonds. That's a big no-no, at least until you get to orgo. And a negative charge on a carbon is a relatively unstable thing in general, and you'll learn that in orgo. The second option is that we have 2 oxygens. So if this H leaves as an H+, it leaves behind the electrons in that bond as well, meaning it'll also have a negative charge. The difference between option A and option B for negative charges is what Jesse talked about, that on option A, one of the lone pairs can migrate and be a bonding pair instead. That would mean 5 bonds to carbon though, so that would mean one of these bonding pairs has to go up. And in essence, what we're saying is that negative charge can be distributed between these 2 oxygens. Hopefully, I saw a majority of people pick that hydrogen. So even if you weren't thinking down that technical level, I hope you were saying, oh, COOH, that is a carboxylic acid. It even has acid in the name. So that is going to be the most acidic proton. The resonance is why. The more stable that negative charge is, the more places it can bounce between, the more stable that form is going to be. So that I just wanted to give you a little bit of insight into organic chemistry that you're going to be doing in the future at some point. But also if you look around a molecule, all hydrogens are not the same. If any of these other hydrogens were to go away and leave its electrons behind, they are not going to be equally as stable. And anytime you put a negative charge on any one of these carbons, it's going to be highly unstable. So that's really a last resort, and you'll only talk about that in organic chemistry. Okay. Our goals, my goals for class today, is that by the end of today's class, and by the way, you probably noticed the worksheet you downloaded, it says 4/22/2019. That's the right worksheet. It is mislabeled because it was from last year. I always start with last year as I modify it and I change the date. I forgot to change the date. So it is not the same thing as last year, but it was based off of that. So you do have the right worksheet if it's 4/22/2019. Okay. I want you to, if there are multiple hydrogens in a molecule, I want you to be able to say there is a carboxylic acid, that hydrogen is most acidic. That's really what I meant by this first bullet point here. But the rest of the class, we're going to spend one, calculating the pH of a buffer before the addition of a strong base or acid, and then after it. Practicing what you had done in your homework, basically. And then we're going to talk about what you did in the primer, which is identifying a redox reaction, shaking some rust off of the wheels. And then we're going to discuss what balancing of a redox reaction looks like. We're going to spend a very minimal amount of time on this in class today. So please make sure that if this is not something that you are very comfortable doing, as if you just did it in Gen Chem 1, that you either go to workshop on Wednesday, where Trip D is going to run you through POGL activity 49. You can do that on your own. Or do whatever you need to do to brush up, because starting Wednesday's class, we're going to assume that everyone is where they would be at the end of Gen Chem 1 with their ability to balance redox reaction, identify a redox reaction, and even do half reactions, okay? So that's a really important thing for me. So identifying oxidizing reducing agent, determining the number of electrons that are transferred. This is all things you do in a typical redox reaction. If you don't have the time or resources or know how to do this, let me know. I'll find some time. We can meet tomorrow or Wednesday if you aren't able to go to Trip G session on Wednesday afternoon. All right. The next thing we're going to do is kind of following up on our homework and post quiz. I want you to look at this solution and I want you to determine the pH of this solution. And then we're going to add a strong something to it and then determine what the pH is after that. So I'm going to send us to breakout rooms. I want you to discuss what type of problem this is, basically what's there, how do we figure out the pH of that, is there a neutralization reaction that occurs, all those kinds of things. And go. Josh, I'm gonna have to send you to breakout room 1. Scared me for a second. It said only one participant. I thought everyone actually like got kicked out of the whole class. All right, we only got 2 clicked in responses. You all still working on this? All right, looks like we got just about everybody back. Only 5 responses submitted. So let's talk through the big picture topics we have to look through here. So how do we start this problem? Can I hear from Sarah Ray? Did you discuss with your group? What did you see in this problem and how did you discuss solving?
We thought you had to find the pKa first, but
Why?
I'm not.
Why would you have to find the pKa? So what is the process that would use the pKa that might be available here?
Or would we have to do the balanced equation first?
That's a good question. Nick, can you share what you're thinking about how to start this and why?
So our group had talked about maybe finding the Ka value first.
Why?
Because we're going to use the negative log of the Ka.
So
that's how we're going to start it.
Okay. So what do you need the pKa or the negative log of the Ka for?
To find the well, I was going to do negative log. I'm not sure what for exactly, but negative log, and then like divide 12 over, or put 12 over 15.
Okay.
Like, so negative log of the Ka value plus the log of 12 over 15.
Okay. So
at least that's how I think.
I like where you're going, and I want to try to be really explicit. There's a number of steps that are happening in the background for you to think that that's the right approach. What are those steps? So what equation is that you're talking about using?
Is that the one that we used last week?
Yep.
The Henson something?
Henderson.
Henderson, yeah.
Hasselbalch. And it's not Hasselhoff. It's not David Hasselhoff. It's Hasselbalch. It's very close, but Germans don't like this equation as much as they like Henderson or David Hasselhoff. So what you're implying there, Nick, is we looked at these compounds and we said NH3 relates to NH4Cl as a conjugate acid base pair. And if it's a conjugate acid base pair and we have a significant amount of both, then we have a buffer. Okay, so these are the steps that I want us to really clearly think through. If it wasn't a conjugate acid base pair and one of these was a strong acid, then we would have to do a neutralization equation first. So let's be really just like methodical about this step. So first, do we have a weak acid or base? Each one of them, or is a strong acid from a base? So we have a weak base. And then here, once this dissolves, we'll get NH4 plus, Cl4 minus. This is nothing as far as acid or base. And this is an acid, weak acid. And these are a conjugate acid base pair. Okay, so those are the first most important things. Once we've established that we have a weak acid and its conjugate base, then we say Henderson-Hasselbalch. And then we say, well, pH is what we're trying to find, equals pKa plus log of the base over, oops, did I do that backwards? I did that backwards, didn't I? 15.0 millimoles over 12.0 millimoles. Can we find the pKa? Okay, we have the Kb, so I think I just calculated Ka times Kw equals, Ka times Kb equals Kw. Found our Ka. And then I found the pKa, the negative log of that Ka. And then I added the conjugate base over acid pair. So I found a pH of 9.352. Does that number make sense? How do I know if I flipped that number? If I flip the fraction, what am I looking for as far as this number? How do I know if this number is reasonable?
Is it from your Ka value?
How so?
The exponent? So the -10?
Okay. So our pKa is going to be very close to 10 to the negative 10. It's going to be between 10 to the negative 9, 10 to the negative 10, which is what you're talking about, which is fantastic. I'm going to specifically compare our pH to our pKa. Should our pH be higher or lower than our pKa?
It should be higher because
Why?
there's more of a base than acid.
Fantastic. So the base has a higher concentration than the acid. If pH equals pKa, that's when you have an equal amount of both, and we know that we have more of the base, so we're going to be on the basic side of pKa. So this number is higher than our pKa, so it's a reasonable value. Okay, those are all the steps I want us to be able to go through. The next question we're going to ask is, now we're going to add some perchloric acid to that mixture. I want to know what the pH is after we add that. So opening up the next Flickr question, I'm going to send you all the breakout rooms, and I want you to think about, like we did, what is this compound? What is the first thing that happens? What do we have afterwards? After anything happens, what is the pH, okay? Think about the steps really explicitly. I'm going to send us all the breakout rooms. Josh, what are you doing?
I don't know. I don't know what goes on. It literally every time I go to a breakout room, it kicks me out and takes like 5 minutes to get back in.
I'm trying to figure out which one you should go to.
I don't really know why, because like no one's on the internet right now besides me.
For some reason, I lost my mouse. PowerPoint. All right, let me try to do this again. Come on. Breakout rooms and assign 7 to 4. All right, go. You really like some dark paint, don't you, Carter?
I feel like an idiot. My mom let me pick it out when I was like 7 or something. And it's supposed to be a lot lighter than this, and then it started drying and it turned almost to purple. I feel like I live in a cave.
Well, you can always repaint. It's not as bad as it sounds.
Maybe one day.
I repainted this office a couple weeks ago, as I was saying. It looks a lot darker actually in the image than it is in person. Mine's like,
Let's say your walls aren't much different than these.
they almost match, except I got a lot, like half of my room is windows, so I don't mind.
Unless I have the windows open, it's dark in here.
All right, y'all. We have 10 responses. So I'm curious, you have a little in the participants window. If you look at the bottom of your screen, there should be a little participants button. If you click that, there's an option to go thumbs up or thumbs down. Can you click the thumbs up if you feel comfortable knowing where to start this kind of a problem? Thumbs down if you feel like you still have a bit of a hard time identifying how to approach a problem like this. And where's my participants window? Why can I not see it? Oh, because it's behind everything. Okay. So if you could click a thumbs up or thumbs down in that window, that'll give me the opportunity to kind of see whether most people are comfortable or not so comfortable. Looks like a lot of thumbs down. Does that sound right? Did I freeze? I froze for a second. So I see a lot of thumbs down. Let's talk about our steps here then. Tracy, can you give me a really high level rundown of what you saw when you read this problem and how you thought you might approach it?
the first thing I saw was the conjugate acid base pair. So I went with Henderson Hasselbalch, and then I just went from there. What I needed to, I knew I needed the pKa, which I could get from the Kb by finding the Ka. And then I solved it from there. And then whenever I saw that we were adding the perchloric acid,
Yes.
that I would have to do the ICF table to figure out how that played out.
So
And then I
pause.
just replugged it back in.
So pause for a second there. When you're saying you saw the perchloric acid and you said you need to do an ICF table, what did you see about perchloric acid that made you think that? And then what do you mean ICF table?
Well, we were adding millimoles to our conjugate, to our buffer. So
what?
We were adding 6 millimoles of the perchloric acid into our buffer that we already had set up.
Right. So what is perchloric acid, and why did that trigger you to say that we need an ICF table?
Because we can only use the Henderson Hasselbalch if we have the conjugate base. So I knew, yeah, and it's a strong acid.
All right. That's kind of what I was hoping you'd get, you'd point out. So once again, if we've memorized all of our strong acids, we're going to see a formula and immediately you want to say, okay, we have a buffer. We have both an acid and a base, and both are weak. And if we add an acid, it's going to react with our weak base. If we add base, it's going to react with our weak acid. So if we can identify that we added a strong acid to a solution that has both a weak base and a weak acid, then this is only going to react with one of those two. And when it does, it's going to do a neutralization reaction. So without a really strong grasp of what our strong acids and bases are, you're going to see something added. You're like, I have no idea what to do. So that's going to be really important to identify and be very explicit about. So what's going to happen to our ammonium is it's not going to react. It's in the presence of a strong acid. We might make more of it, and we'll keep that in mind. So the way that I wrote this out is our strong acid, every one perchloric acid dissolves and releases one H+. And when it does that, it consumes one NH3 until either the NH3 is used up or until the H+ is used up. And our big question is which one is going to run out first. So you can either call this a limiting reagent problem, or you can use an ICF table to help you calculate that limiting reagent problem. So I wrote this out and I said, well, how many millimoles of all things do we have when we start? We have a weak base, we have a strong acid. Note the arrow that I used here, that this reaction goes to completion. Anytime we have a reaction that goes to completion, that one has to be identified and done first. We might have an equilibrium reaction later that we'll look at. We might, I don't know if I froze there. We might have an equilibrium reaction we're looking at later, but any full-headed arrow always has to be completed first. So in doing this, we're reacting at a 1-to-1 ratio. Every one H+ uses up one NH3 to make one NH4+. So what's going to be our change? Let me ask Stacy to fill in the change row here. What's going to be the change in the number of moles of each of these across from left to right?
The ammonia is going to, or on the left side of the equation, you would subtract 6 millimoles, and on the right side, you would add 6 millimoles.
Great. Every one used up on the left produces one on the right, and we can only use up as much as the smallest amount that we have. So our H+ is our limiting reagent in this case. In the end, I think I have it more formally written out. We use up all the H+, so that's going to be 0 in the end. And we have 9 millimoles left of our NH3. In the process of doing that, while we started with 12 millimoles, we added to that with every one of NH3s that was protonated in the neutralization reaction. So we have a total of 18 millimoles of our NH4 plus. So what do we have after we're done? That's the next most important question to ask. So Kat, after we get to this point, the final amounts of everything after the neutralization reaction, what kind of a reaction or what kind of a mixture do we have? Is it a weak acid, weak base, buffer, strong acid only, strong base only?
After you've used up all of the, like after you've used, after the change with your final, you have a weak base and a weak acid because you've used up the 6 millimoles of the hydrogen in the acid. Is that, oh, 18, okay. 18 and 9, so you're.
No, you're right. We used up the
Okay.
6 millimoles of our H plus ion. That's what you're referring to.
Mhm.
So we have a mixture of a weak acid and a weak base. And what do we call that?
A buffer.
Great. So you probably saw in your homework and the post quiz that sometimes when we do this, we're actually going to run out of the weak thing first. So if 15 had been less than 6, we would have used up all of our weak base and had extra strong acid left. Or we might have had the same number of moles of both, and that's the equivalence point. So a titration, especially of a buffer, is really just thinking about what do we have in solution at the start, what's going to react, and then afterwards, what do we have? In this case, because we have a buffer afterwards, Nick, how do we solve for the pH of a buffer?
For the pH of a buffer?
Bringing it back to you after that last question.
Is it similar to how we did it earlier in the problem? Or in the last problem?
Yo.
You always take the negative log of that pH? Oh, I'm sorry, not the pH, but we're trying to find the pH of the buffer. So I guess whatever the buffer would be.
What equation do you use for buffers to find the pH?
The same one we just used?
Yeah.
Yeah.
So the Henderson-Hasselbalch equation, if we have a mixture of a conjugate acid base pair and we have a decent amount of both, then we can use that. We started out with the pH higher than pKa because we had more of the base than the acid. Is that still going to be true? We expect the pH to be higher than the pKa now.
Oh, the pH?
Yep.
Shouldn't it be lower?
Why?
I mean, we added a strong acid.
True, but that alone doesn't tell us. We need to look at the ratio between these two. If we have an equal amount of both, the ratio is 1:1, our pH is going to be equal to pKa. In this case, it's not. We shifted from having more of the base to now we have more of the acid in the conjugate acid base pair. So our pH is going to be more acidic than pKa. So always think about your checkpoints. Where are you going to be comparing your values to? And I think on the next page, no, I didn't actually write it out there. Looks like. So in the end, let's see, can I have Patrick, how do we actually calculate the pH of this final solution?
I'm thinking.
You want to pass on this one?
Yeah, I'll probably have to pass on this one. I'm not sure.
Alex, can you help us finish this? Alex, you're muted right now. I'm not sure if you have access to be able to chat with us. Maybe we can try Taylor Gamble. How do we find the pH of this final solution?
Okay, so since we have the final millimoles, we can convert those millimoles to a molarity or concentration by dividing the 9 by 300 milliliters and the 18 millimoles by 300 millimeters or milliliters as well. And then once we find those two concentrations, we can plug them into the Henderson-Hasselbalch equation, and as well as our pKa to solve for the pH.
And here's the shortcut that works really, really well. Because you're going to be doing your millimoles over 300 mils on the top and the bottom, the volume in this one equation cancels out.
Okay.
That is not true for your Ka equation. Ka, you have to use concentration. You can use it here as well. But if you want to save yourself time, then what I would do is I would just put the concentration or the number of millimoles of the base over the number of millimoles of the acid. And that calculation will give you the same value as if you had concentration of 1 over the other. So if we do that, we're going to end up with a pH, what do we got? 9.255 plus log of 0.5 is, so I get a pH value of 8.95. That's probably as many sig figs as we should do. So pH is lower than pKa. That's good because we have more of the base than the acid for that particular conjugate acid base pair. The pH went down when we added a strong base. That also makes sense. But we have to be careful, and we're not going to say pH is lower than pKa because there was a strong acid added. Because if we'd only added 1 millimole of a strong acid, our ratio would be 14 to 13, and we'd still be more basic than pKa. So just be really careful about your final number of moles is what decides whether pH is higher, lower, or equal to pKa. All right, any questions on how we worked through this problem? This is one of the more challenging problems, not because of the math, but just deciding what to do when. If you're not super comfortable with this, this is a perfect thing to do office hours with. I just had a few people with us before class, and we did office hours, and we worked through a number of examples of this, and I think people built up some confidence. So make sure to find me, and we can work through some examples of this. Any questions before we move on? Lots of quiet faces. You feel a lot more hindered to ask questions when it's this many people staring at their screens. I feel like there's many fewer questions. I greatly do appreciate it. If you have a question, it's most likely that many of the other people in the class have questions about the topic. So please don't hesitate to ask questions.
Is there any time you will use molarity instead of moles in this equation? Because I don't know if I'm just remembering wrong, but I believe in some of the primers they had us use molarity instead of the moles, or maybe it had us convert molarity to moles. I can't remember.
In order to do the limiting reagent problem component of a problem like this, you have to use moles. And a lot of times it gives you molarity. So you have to convert to moles. In a table like this and using Henderson-Hasselbalch, you can always use moles every time you use the equation. And the reason is because moles, it's molarity over molarity are the units of concentration. They're always in the same solution, so they're divided by the same concentration or the same volume. The time that doesn't ring true is when we do an ice table. If you use an ice table, then you have you kind of see our Ka equals x squared over initial minus x. The units on top are moles squared over liters squared. And on the bottom, we have moles per liter. Those units, you cannot just put moles in. It does not work, it falls apart. So for Ka, you have to use molarity only. Okay, so if you did a titration like this of a buffer and you ended up with a weak acid only or a weak base only, and you had to do an ice table to solve for the pH, you have to then find concentration. Good question. So there are some more practice problems at the end of last class's slides that we didn't go through all of them. And then end of this slide deck that I'll post after class, there are also more questions there on doing titrations and buffer problems. So make sure to work through those. There are also a few POGO activities that we posted. If you look at the schedule, it has them listed, which ones will help you kind of work through practice examples. So for this part of class, we're going to spend just a couple minutes talking about our equilibrium constant in a third example. So originally we talked about just equilibrium as a whole, Kc. Then we talked about equilibrium for acids, specifically that dissociation of a proton. And then now I want to spend about 15 minutes talking about Ksp, solubility. It was in your homework, and I think one of your primers, is that right? Have you been working on Ksp? Yeah, I saw a little bit of it. So the idea is that if you have ions floating around, just like we talked about, an H+ ion and a base, those things can come together and they can disassociate and they can come together. Those usually stay dissolved in water. Sometimes when you have ions like that that come together, when they come together, they actually push all the water away and they become heavier than water and they precipitate out, meaning they float down as a solid. They end up at the bottom of your solution and they are now separate and not fully dissolved in solution. That's how all these gems are formed. So you can see anytime you go into a cave and you see mineral deposits, that's usually some form of calcium. A lot of the different stones and gems you see, those are ions that were dissolved in water. And when they happen to find another ion that was the opposite charge that they were very attracted to, they'd come together, they'd fall down. And depending on how slowly they settle, they can actually form these crystals that are gems. So based on what you know of solubility, I want you to look at that beaker there, and I want you to tell me which of these three options could be appropriate for what's in that beaker right there. And there's some definitions on the second page of your worksheet for tonight on what soluble, slightly soluble, or insoluble compounds mean, which is a little more detailed than you probably have seen in the past. Couple more seconds. All right, closing out. Can you guys see the results when I put them on my screen like this? I wish I'd known that before because I was trying to like hide them from you guys so I can see them. I'm checking on my phone to see the results. Turns out you can't see them. That's amazing. Okay, good to know about Zoom. All right, so we have a mixture of responses. Can I hear from someone who answered C, why they think it was C?
I just said C. I wasn't really sure, but I just said C because the solid was at the bottom of the beaker.
Okay.
So.
Great. Someone answered D. Can I hear from you?
I said D because even if it is soluble like table salt, there's only, if you have a limited volume of, say, water, only so much can dissolve into it.
Yeah. And I like both of those descriptions because we can think about if you just pour, if that's how much we poured into the glass, then I would agree. It looks like my internet is choppy. Did I cut out there? Looks like you guys froze too. If that's the total amount that we poured into the beaker, it would make sense. I would agree with Nick. But we could have poured in twice that much and some of it's dissolved. So what I want us thinking about is that we can always describe that equilibrium between the dissolved and the solid, and we can use a number to describe that. So for this one, I would say that D is the appropriate answer for this, that we could have a lot that's already dissolved. Like, you know, you can pour table salt into water until it's super saturated, and then we can add more, or sugar or something like that, right? So this table that we've used previously in the semester to determine the solubility of salts, I want you to take this with a little bit more of a grain of salt. I want you to think about these as white doesn't mean it dissolves until infinity, right? It means it dissolves over 0.05, is it 0.5 molar? What did I have on that worksheet? 0.5 molar? So that means it's highly soluble. And then there's this kind of soluble range as well, which is greater than 0.05 molar. And then there's insoluble. And let me see if I'm on the right Wi-Fi network. I am. Why is it not working? My internet connection is sketchier than I'd like it to be. So this idea of insoluble doesn't really mean that nothing dissolves. It just means that it's a much lower concentration that goes into solution. And so we can describe what that is, right? We can say we have a solid, and then on the product side, we have the ions. And based on our knowledge of equilibrium, we can say, well, what's the equilibrium constant? Meaning, what's the likelihood that those products are going to form? So we have these definitions. 0.5 molar or greater is soluble, between 50 millimolar, 0.05 molar, and 0.5 molar is slightly, and then insoluble. So we've kind of been lying to you before and saying it's either soluble or insoluble. That's why I really don't like you memorizing these rules. So there's a spot on your worksheet. Go ahead and write out the equilibrium constant K, specifically KSP. Let's do KSP for this reaction here. Go ahead and take 30 seconds to write out your equilibrium constant. And can I hear from Miss Taylor Arnold? What do you have as your equilibrium constant?
I said KSP equals the concentration of silver times the concentration of chlorine.
And I'm just going to make slight tweaks to your statement. I'm going to say the concentration of silver ions times the concentration of chloride ions. Because in your homework, I think it was really particular about calling it an ion or the name of the element. And so that wording is pretty particular. And here, if you said the concentration of silver, we might be referring to silver solid, which is not what we're talking about. All right, so I'm just going to be pretty picky there. So why do we not include silver chloride in the equilibrium constant?
It's a solid.
All right. So for KSP and for KA, for both, we don't include solids and we don't include the liquid, the solvent that it's in, so water in this case. All right. So this KSP is a solubility product constant. So which of these two salts is more soluble based on the KSP values you see there? And I think this is one of your questions on the back on the second page of the worksheet as well. It's listed there, so you have them in writing. Couple more seconds. Closing up. All right, we have an overwhelming majority saying that it is B. Why? You've never seen these salts before. How do you know that B is more soluble than A? Aislinn, what? Why would B be more soluble than A?
I thought B would be more soluble because the KSP is bigger.
What is that?
So I thought that the concentrations were going to be bigger. I don't know. I looked at it and I thought about it, and then in my head when I'm trying to explain it, it doesn't make sense.
No, you're definitely on the right track. Carter, are you raising your hand? Or are you scratching your nose? You're muted.
I have a guess maybe, and it's because since there's a bigger number, KSP is bigger, that means more of the ions dissolved.
Yep. So kind of combining what both of you said is that the larger KSP is, remember KSP is the concentration of one times the other. So the bigger that number is, the bigger the concentrations are at equilibrium. So you could put blocks, tons and tons and tons into water, and very little of it might dissolve, and you'd have very small concentrations like the top one. But if you're talking about zinc iodate, then 10 to the negative 6 means you're going to have a lot more of each of those dissolved in solution. All right. So let's take that and that idea that as your KSP gets bigger, your solubility is bigger because it's concentration of products only. The bigger the number is, the more concentration of products you have. And let's go ahead and figure out what the solubility is of iron hydroxide. So I've given you the KSP. I'm going to send us into breakout rooms for a couple minutes. I'm going to do 3 minutes. Think about what you've done and learned with equilibrium. This is just an equilibrium problem. So many people are like, oh no, it's a new K. I don't know what to do. You know what to do with K. Concentration of products over concentration of reactants. Make sure they're to their stoichiometric coefficients. You can do this. All right, we're gonna come back in 3 minutes. I'm gonna send us to breakout rooms now. Hello, hello. Am I muted still? No. Okay. Turns out there's a shortcut with the keys. Command-Shift-A. It unmutes you. All right, I have 5 responses. How are we doing on this? All right, almost everyone's back. Everyone is back. All right, so I want to hear from Sam. How did you approach this, and how far did you get?
I'm honestly still kind of confused, but we were talking about how we would initially set it up, and that it was similar to some of the equations before. We did get to the final setup of the KSP value, that's 4.87 times 10 to the negative 17 would be equal to 4x cubed. And that's as far as I've gotten.
Okay, so how did you get to that value? And we might tweak it a little bit. What was the major step that we had to do?
Still kind of lost on that part.
Okay, so everything we've done, repetition, 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 is ice tables. If we're talking about something going to equilibrium, we're always going to do an ice table. Some of the stuff we did with buffers, we had a neutralization reaction first, but then many times we do an ice table afterwards. So here, any KSP problem is just the same. It's still in equilibrium. We're still doing concentration of products, raise the stoichiometric coefficients divided by concentration of reactants, raise the stoichiometric coefficients at equilibrium. But in this case, we don't have any concentration of the solid. So that's out of the equation, right? We just talked about writing our KSP. So what would the formula be for KSP equals concentration of products over reactants? What would that expression be for this reaction?
Is it the concentration of Fe, yeah, iron 2+ ion, and the concentration of OH- ion raised to 2?
Great. That's going to be extremely important. So regardless of what happens in the ice table, we always know that our KSP is going to equal concentration of products raised to stoichiometric coefficient times each other. So keep that in mind. That's not going to change. The question is, what is the concentration of OH- at equilibrium? And so that's where the 2 comes into play again. Not only the stoichiometric coefficient, that's the exponent, but also in the concentration. So if we go ahead and fill in the table, we're basically saying, okay, we don't have any in solution. What is going to form? And so we used X's before. I just put S here because a lot of times you'll see solubility and people use S because they like to use S. It's the same thing, X, S, whatever you want. It's a variable. Every iron hydroxide that dissolves generates 1 iron 2+ ion, but it also generates 2 hydroxide ions. So at equilibrium, you have X and 2X, or S and 2S, whatever you want to call them. So then we have to go back and plug those values into our equilibrium KSP, exactly as they are, and don't forget about the exponent as well. So we have our concentration of iron at equilibrium, our concentration of hydroxide at equilibrium raised to the 2nd power. So 2 squared is 4, S squared is S squared. So we have 4S squared times S. And that comes out to 4S cubed. So that all equals KSP, which we have a number 2 up at the top. So how do we then solve for our solubility, the molar solubility, this S thing or X, whatever you solve for?
Hey, Dr. Bailey, I'm still not seeing how you got the 4S squared.
Okay, so if we do 2S squared, then we square everything inside. So we square 2, we square S. So that's 4S squared. You okay with that? And then we multiply that by S again, and that's 4S cubed. Cool. All right, I'm gonna erase that to give myself some more space. So then once we have 4S cubed equals KSP, we divide KSP by 4, and then we take the cube root of that. How do you feel about doing cube root in your calculator? Comfortable with that? Know how to do that? So there's usually a function on there somewhere that's like X root of your value.
You can also like raise it to the 1/3 power.
Yep.
That's always what I do. That's easiest.
Good
or at
call.
least to me.
Very good call. So we
I
could
have a
do.
question.
Go ahead.
So when it's asking what is the solubility, it's asking for X basically.
So in this case, the molar solubility is X. if you notice the terminology here, it said this one was in grams per liter. Is that the same thing? Yes, no, Sydney?
Yes.
No.
Nope, just kidding.
So big M, remember, means moles per liter. And so if we want grams per liter, how do we convert from moles to grams? Molar mass, anybody? All right, we're feeling a little sluggish tonight. So the concentration at equilibrium, we could calculate those. We could also say the solubility of iron hydroxide was that X value that we found. But that's moles per liter. So if we did want to convert to grams per liter, we would use the molar mass to convert from moles per liter to grams per liter. A lot of times in geological applications, they'll ask for the solubility of a substance, or they'll tell it to you in grams per liter instead of moles per liter. So the last question on this that I had was, I'm going to go ahead and close this out. I'm not too worried about the last step. If you could have found X in that whole ice table, that's the most important thing. And then converting from that to different units, I think it just wasn't clear. Maybe you're straightforward. So then what if we did this same problem, but instead of starting with 0 for one of them, what if we started with some iron ion in solution? What would be the same and what would be different? Thoughts? What would be the same and what would be different if we started instead of with 0 for iron in solution? Maybe it was a solution of iron nitrate or something. So we already had some iron in there. How would that impact this reaction? Would it make it more soluble, less soluble? And then how would we calculate that? Anybody? Anybody?
So it would make it less soluble, right?
Why?
Because there's already some of the iron ion in the solution, Le Chatelier's principle and all that.
Perfect. So if we have our KSP equals the concentration of iron times the concentration of OH minus squared, we're basically saying we already have some of this. So that's going to have to drive down how much of it can be produced. So the way that we would calculate that would be an ice table, but we would start with the amount in there instead of 0 for one of them. And then we would do the exact same thing. But now, is there a way we can do this without being super complicated? Do you think? Maybe, maybe. Let's make the assumption. Let's see, maybe the assumption will work. Less than 5%, right? That simplifies our calculations a lot. And if we take and we find our molar solubility, we can go and then check to make sure that that number is less than 5% change in our initial value. It is 10 to the negative second, 10 to the negative 8. That's a big difference. So what that tells us is the amount of iron hydroxide that could dissolve in the solution is much less. And we can calculate it just by doing an equilibrium constant. So the the take-home point is, regardless of your type of equilibrium calculations, if we're doing an equilibrium reaction, an ice table concentration of products, the stoichiometric coefficients over concentration of the reactants is always going to be your approach to solving for what the concentrations are at equilibrium. We could then go ahead and calculate grams per liter as well by using the molar mass like we did that last problem. Okay. The last question I have for us today in class is, what type of reaction is this? I'm going to make a statement that this is a redox reaction. I want you to say whether that is true, false, and I want you to identify how we know that it is or is not a redox reaction. Twenty more seconds. All right. And with that result, I'm going to say that at least a third of the class, if not half the class, needs to brush up on redox reactions before next class. That's the big take home from this. This is a redox reaction. The ways that we can tell, which this alone might help brush off some of the rust, but make sure that you, if you're really rusty, go to the workshop 4:30 to 5:30 on Wednesday if you can. Review however you can. Come work with me. Read the book, whatever you need to do. This is like chapter 7 in our book, or 8 or something like that, or maybe even earlier than that. It's like first semester stuff. So the biggest way to tell is to figure out the oxidation numbers. If you can't remember how to find an oxidation number, that is an absolute must. Very similar to finding formal charge, but it's slightly different. It's about the more electronegative atom gets to count any bonded electrons towards its valence shell. And it's about comparing valence electrons to non-valence electrons. If we have something changing from an oxidation number of 0 to an oxidation number of +3, that means it's losing electrons and it is oxidized. So I always say Leo losing electrons is oxidation. Leo the line goes GR. Losing electrons, oxidation, gaining electrons, reduction. So Leo the lion goes GR. If you have your own way of remembering that, that's fine. So aluminum loses electrons. It goes from 0 to +3. Electrons are negatively charged. Lost 3 for every aluminum. That means that that one is oxidized. Hydrogen, on the other hand, goes from a +1 to a 0. That means it gains electrons. That means that is reduced. So make sure you know what is oxidized, what is reduced, what's an oxidizing agent, a reducing agent, how to do half reactions. There's a reason this builds on semester 1. And so I'm expecting you guys to work on that on your own, or I'm happy to help you tomorrow or Wednesday if you can set up a time. Just send me an email, we can work through that. All right, that's all we have time for tonight. Feel free to stick around if you have any more questions, and Humendra is going to help you through your last lab tonight. So see you soon.
Thank you, Dr. Bailey.
Dr. Bailey?
Yep.
Quick question. On the last